So often, and I would almost say usually, as we move forward, it's going to be more convenient, more useful, easier to work in a different coordinate system than rectangular coordinates. Rectangular coordinates, we end up with these square roots of things, and we have to do a trig sub, which essentially trig sub is changing to polar coordinates in essence anyway. So we want to do it up front to make our lives easier. All right, so just a reminder about the structure of polar coordinates. Here is our setup. We have a point out here in the plane, and we're going to label its coordinates r theta. Theta is the angle measured counterclockwise from the horizontal axis that we're going to call the polar axis. This distance from our origin, which we're going to call the pole, is our r. And we'll call the vertical axis, I'll draw that in a dotted line, like so. The vertical axis we're going to call the pi over 2 axis. So the origin is called the pole. The polar axis is the same as corresponds to we can also call it the theta equals 0 axis. So they kind of use those interchangeably, the theta equals 0 axis or the polar axis. This is just the pi over 2 axis. R is the directed distance from the origin to the pole, so we can have our radius be positive or negative. And theta, the positive theta is measured counterclockwise from the polar axis. R theta, unlike polar coordinates, is not a unique representation. So the reason for that is because our theta, we can rotate 2 pi units and get back to the same point. So that point is equal to r comma theta plus 2n pi. 2n pi just represents a revolution of a full circle around. Or r theta, remember we said that the radius, the r value, is a directed value. We could go negative r and theta plus 2n plus 1, an odd multiple of pi. And we can think of a negative r as going kind of in the opposite direction from the angle where we're located. So if we're at pi over 4 here, we could be at 180 degrees or pi radians here and call that a negative r. So we go in the opposite direction to get to the same point. And the pole, one tricky part of polar coordinates is 0 theta for any theta. So if our radius is 0, we're at the pole no matter what our angle is. So when we're analyzing curves, when we're looking for tangent lines, when we're looking for various things, we have to remember that anytime we're at r equals 0, we're at the pole. All right, questions on our setup here. This shouldn't be new material. Should be more or less review. What we're going to be interested in this section is 2 things. We're going to convert coordinates, and we're going to convert equations. But as we move forward, the more that you can think in polar coordinates instead of having to transfer back and forth, the easier they're going to be to work with. All right, so our coordinate conversions come from taking our little drawing that we had here. So this is our theta equals 0 axis. This is our theta, and this is our point, our theta, or x, y in rectangular coordinates. And we're going to turn this into a right triangle. And this is x, and this is y. So from right triangle trigonometry, we get that x equals r cosine theta. Y equals r sine theta. Just from this nice right triangle there. Tangent theta is y over x. And r squared equals x squared plus y squared from the Pythagorean theorem. So those are our conversions. So let's do some conversions. First, we'll convert some points, and then we'll talk about graphs and equations. So we have that r theta is 2 pi over 6. We want to convert to rectangular. Going to rectangular is usually the easiest. X equals r cosine theta. So that's just going to be 2 cosine pi over 6, which is cosine of pi over 6. Square root of 3 over 2, which is just square root of 3. And y equals r sine theta. So 2 sine pi over 6, which is 1. So we have that 2 pi over 6 is equal to square root of 3, comma 1. All right, let's go the other way. This can be a little trickier. So we have x, y in rectangular coordinates is -1 square root 3. And we want to go 2 polar. So what we have to be careful with here is what quadrant are we in? Second. So we need a second quadrant angle. So we need theta in the second quadrant. So when we look at our theta value, we need to be careful. Tangent theta is y over x is square root of 3 over -1. So just negative square root 3. So we need a second quadrant angle whose tangent is negative square root 3. So if we have a pi over 6 angle, we have sine over cosine, right? So we have square root of 3 in the denominator. So what? So so if we have a pi over 6 angle, we get square root of 3 over 3, right? Well, we have a 50-50 chance, right? It's either a pi over 6 angle or a pi over 3 angle. So what is this one? Theta equals, what did we decide? 2 pi over 3. And so our radius r is the square root of -1 squared plus square root of 3 squared, which is 2. So we have -1 square root 3 equals 2 pi over 3.
Are we going to ever have x and y values that aren't on the unit circle?
Possibly.
So then we might actually have to do tangent.
Right, an inverse tangent, and then get it in the right quadrant. Because your calculator is only going to give you an inverse tangent between -pi over 2 and pi over 2. What if we wanted our radius to be negative? -2, comma, what would our angle be then?
Well, negative 5 times 3.
5 pi over 3 or -pi over 3? So either of those would be a representation, and there are others, there are an infinite number, but those two would be representations of that point in polar coordinates. So we could say this is also -2, comma, -pi over 3. All right. Polar graphs. Usually with polar graphs, where if you're required to graph a polar graph, you're going to be using your calculator. So your calculator in polar mode, make sure you're in radian mode as well to make these graphs. You will get familiar with some of our common polar graphs: circles, cardioids, lemniscates. And there is, so graphing manually is tedious and time consuming. You have to construct a table of values, and it's on the challenging side. So usually we're going to be using our calculator. In your book, there is a table, and we had I gave our class a similar table in pre-calc on page 721 that has a list of common polar graphs. And the ones that we should be familiar with, or that we will get very familiar with, are circles, cardioids, and lemniscates, and rose curves. But as we'll see, as we see them more, we'll start to recognize them. All right, so let's talk about some conversions with equations. Let's convert to rectangular. First. R equals A, where A is a constant. First off, what is this thing? Circle, radius, A, center, 0, 0. So what would the equation of this be? X squared plus y squared equals A squared. If you didn't see that right away, you could square both sides of this. R squared equals A squared, and R squared is X squared plus Y squared. But that R equals A, something that should jump out, oh, that's a circle, radius A, center at 0, 0. How about theta equals pi over 6? It's a line. Slope. Yeah. Right. Square root of 3 over 3. And to see this, we could say tangent theta equals y over x. And so tangent of theta is square root of 3 over 3. So we get y equals square root of 3 over 3 x for the equation of that line. So line through the origin with slope square root of 3 over 3. Slope, the tangent of theta gives us the slope. A little trickier. R equals secant theta. Yeah.
1 over cosine theta, and you could multiply that across and get r cosine theta.
Right. So this is r equals 1 over cosine theta. And then we can multiply across. R cosine theta equals 1. So x equals 1. Sorry, that should be 1. I was thinking one step ahead. R cosine theta equals 1, so x equals 1. So that is a vertical line. So sometimes rectangular coordinates are nicer.
How
Sometimes
is r equals secant theta nicer than x?
no, x equals 1 is nicer in this case than r equals secant theta. But r equals a is nicer than x squared plus y squared equals a squared. I would argue. And when we go to evaluate integrals, r equals a is going to be nicer than x squared plus y squared equals a squared. This would require a trig sub. This won't require a trig sub. All right, let's look at some other equations. This is where it gets interesting. R squared cosine theta sine theta equals 4. Yeah, when we're converting these, we look for opportunities to compare to pair r's and sine thetas and cosine thetas. So we could rewrite this as r cosine theta, r sine theta equals 4. Whoops. Again, I'm thinking a step ahead. R cosine theta is x. R sine theta is y. xy equals 4. So what is that thing?
That's one of these.
It's a hyperbola.
Yeah.
I knew what you meant, Connor. So r squared cosine theta sine theta equals 4 is a hyperbola. How about there's an a b. R equals 1 plus 2r cosine theta. Well, we could substitute x, but let's square both sides. Let's get an r squared, because r squared is x squared plus y squared. So r squared equals, when I square this, I get 1 plus 4r cosine theta plus 4r squared cosine squared theta. Oh, that looks nice. R squared is x squared plus y squared. This is 1 plus 4x plus 2x squared. And I could rewrite this as, we could leave this as 4x squared. That's fine. And I could rewrite this as y squared minus 3x squared minus 4x minus 1 equals 0. Do we know what that is? Yeah.
Could you have also written that when you set the r, can you write that as square root of x squared plus y squared?
Yeah, you could do that.
Okay.
Yeah. I usually think, I try to avoid the square roots just when I think about it, but just, you can do it the other way. Do we know what this is? It's a conic section, yes. The signs on x and y are opposite.
So it's actually
It's a hyperbola. When the signs on the x squared and y squared are opposite, you have a hyperbola. How would we see what the center is and all of that kind of thing?
Solve by trying.
Complete the square on the x part to see the shift.
Great.
All right.
Trying.
This is so yeah. This is it's always nice when we get to this part in calculus because often students say, oh yeah, we really didn't learn that much that was useful in pre-calc. But we get all these conic sections back and it's fun. R squared equals 4r cosine theta. That one's not bad, right? X squared plus y squared equals 4x.
No, that's not it. That's why.
No, it's not. It's a circle.
What is that?
It's a circle.
This is a circle. And to see where its center is, we could complete the square on the x part. X squared minus 4x plus 4 plus y squared equals 4. So we get x squared, x minus 2 squared plus y squared equals 4.
So
Centered at 2, 0, radius 2. And here we get a clue about the radius here. Usually you'll see this equation written as r equals 4 cosine theta. Then it's easier to see as we get more familiar with polar coordinates that this is a circle, radius 2, and it's shifted on the x-axis because of the cosine theta. Remember, if you remember back in pre-calc, we said when we had polar equations that just involve cosines, that we had polar axis symmetry. All right, let's look at one more. R equals 4 over 2 cosine theta minus sine theta. Multiply both sides. So we get because r, 2r cosine theta minus r sine theta. I'm going to distribute it at the same time equals 4. That's a line. This, I would say, is nicer than this. The rectangular version is nicer than the polar version. Yeah, polar coordinates are nicer for curvy things. Rectangular coordinates are nicer for straight things. They are nice. Polar coordinates are nicer for curvy things. Spherical coordinates are way nicer for three-dimensional curvy things. Three-dimensional square things are really messy. All right. Three-dimensional polar coordinates are cylindrical coordinates. And then we'll do no, that's next unit. We'll talk about cylindrical and spherical coordinates. Yeah, when we in chapter 11, we'll free ourselves from the plane.
There's a lesson called Vectors in Space, which sounds
Yep. Yeah, when we start combining vectors and cylindrical coordinates. That's really nice.
Oh, wait a minute.
No, was he gonna be here?
There we go.